Hello, everyone. It's a great pleasure to support this fantastic initiative by Nemetschek Foundation and TU Munich, the new Institute for Artificial Intelligence in the Built World. And I would like to thank Professors Ernest Rank and Andre Bormann for inviting me. Also, I should mention that due to vast time difference between Europe and Australia, my talk is pre-recorded. So in the world that is increasingly converted into information, seemingly intractable problems are now being addressed with the ideas of complexity science. Complexity science is not a new idea. It's been around for a while, but recently it's empowered by the computational processes based on big data and AI. And of course, cities are the most complex constructs humanity has ever built. Yet our adjacent fields of architecture, engineering, city planning, construction are still not working on the problems of cities and buildings or seeing them as problems of complex systems. So this has been at the core of my work from the very beginning, this question: how do we build for complexity using all the resources of computation we have today? And of course, I started looking into these new resources that clearly are transforming so many other fields and facets of our life. So accelerated computation, high volumes of computing, availability of big data. So this landscape of information, how can that provide some new resources for rethinking our fields and built environment as a whole? Especially because design is, I always think if there is one superpower of design, fields like design and architecture, it's this power of complex synthesis of myriad of agencies. I think it's a natural ability of these fields to synthesize because they have always been doing so. But today, this capacity is accelerated by availability of big data, computational resources, and AI. And we can now, instead of just metaphorically or aleatory, we can now explicitly bind micro to macro conditions of the built environment, and also build a bridge between disparate disciplinary knowledge or pockets of isolated pockets of expertise. That is also largely due to the shift of all these disciplines from the classical ones such as chemistry, biology, engineering, architecture, to the ones run on the fabric of computation, such as computational chemistry or computational architecture. That computational layer is what allows us to build that bridge. And so I invested most of the focus of my work on what I entitled logical core of architecture, or these patterns of correlations. Now, the patterns of correlations, so shift from causations to correlations, is something that also opened door to big data and AI in my mind. And I've really been consciously working on restructuring on these logics at the core of all these synthetic processes to algorithms that are increasingly discrete, and again, shift from maybe mathematics to computational models, especially nonlinear ones and more open-ended ones, allowing for open synthesis. So the big data architecture ability to connect with agencies, explicitly connect to myriad of agencies that are outside of just pure, for instance, design process, and also exciting opportunities or new, you could say, design collaborators such as physics, so co-designing with physics directly due to simulation and in general bringing more science to buildings, which I think is imperative now. And since I always like working from the first principles, one of them from the very early on has always been high resolution, because very early on I recognized that what complex systems in nature have in common with some of the most advanced examples of current technology is this idea of high resolution, high populations. We see entirely different things when we increase the resolution. And so if we, for instance, apply that to construction of buildings, we all know that buildings are at least 10 times heavier, the contemporary buildings, at least 10 times heavier than laws of physics are telling us they could be. So of course, in nature, we don't see that. Nature does not waste material. And so could we reach such high level of performance, or I like to call it super performance, more resonating this kind of complexity and super performance we find in nature, for instance, in our own bones, if we use this abundance of information and new resources. And also in constructibility, introduction of automation and robotics, universality and precision of robotics allows reprogrammability of these processes, and it opens exciting and quite massive territory for innovation in construction. So you can, for instance, teach your robots to see through deep learning, through, again, machine learning, to learn what the node is, so that radically accelerates speed of printing, also its precision, or even any kind of possibility, because we know that these materials, they're volatile and non-linear. So it's necessary to develop this real-time feedback and adaptation in the process of construction. Briefly, just a project that I designed for the Venice Biennale in 2018, Croatian National Pavilion, in collaboration with ARUP, and also manufactured by a startup that came out of my research lab at UCL in London, so AI Build. They're doing very good work in software for 3D printing. And so this is, for instance, a structure that is 8 by 8 meters in plan and 3.5 meters tall, and only weighs around 275 kilograms. And it's incredibly strong, even though it's printed in very weak material, just recyclable polymers. But because of the redundancy, extremely high resolution of this network of connections, there are 40,000 voxels in this structure, these cells, microcells. It's really resilient and strong and ultra light. So that idea of intricate structures extend also in our research with, for instance, other materials that are more substantial for construction and buildings, such as metals and metal alloys. So looking into cold spraying of metals with CSRO here is in Australia. Also, we collaborated with Titomic, and being able to design at an extremely high resolution, molecular resolution, you could say, because now you can program different molecular densities in different parts of structure, therefore different weight and strength of the structure, and heterogeneity of materials, because there could be different types of metals and metal alloys in different parts of structure. So then what kind of architectures and buildings can be envisioned, how they can perform with light, with heat, with spatial experiences, with organization, with ultralight structures, etc. If these are the details of your buildings, rather than ones that thousands of times lower res that we currently use. So apart from quantitative shifts, what kind of qualitative shifts can we also see in this high resolution fabric of buildings? What is possible now? But of course, when you work with such high resolution design, there are lots of glitches because you are trying to cross a new threshold, encountering slow resistance of matter. So, for instance, this was a field that I designed for Venice Biennale initially with 1,000 voxels. In the end, we printed only million voxels. In the end, we printed only 40,000 because of the available time that we had and the nature of this robotic extrusion. So through simulation, we calculated that that was the maximum, and therefore we worked with that kind of constraint. There are various other challenges because when one is trying to design search, and design search is really has been my focus for many years now. How do we design search to such highly informed field? So if you, it's kind of like going diving into the ocean and trying to discover this exciting creature. So you go into this n-dimensional space and encounter cursor dimensionality when you exceed certain number of parameters. So capacity to find certain productive or exciting, I would say, instances of designs, of useful designs, exceeding human capacities of human cognition. So it's necessary to, again, introduce this AI partnership as another kind of cognition, in fact, a very different one than ours, to assist in this design search process. And so when the information is abundant, picking a pattern becomes a work of the machine, I would say. And then this was an example, just quickly, of supervised learning in collaboration with Andy Lomas, who was part of my research lab in London at UCL. And interesting thing about this interface is when different designers work with it, it acquires different biases, different aesthetic biases initially. And then later on, also introducing other parameters such as evaluation, in terms of physics or structural properties or curvatures, and resolution, and similar different materials. So it really inform a vision of an informed design search, and we are developing all these different bits and pieces of such platforms. And also it has always been my interest to look for novel aesthetics as well, something that we were never able to see before. So rendering invisible visible. So what can we discover also in aesthetic domain? And again, that was not possible before. And now jumping into a different challenge, because again, as I said, I see built ecology truly as ecology, and every ecology includes a multitude of problems or challenges, but also different orders of scale. And so we are probing these different questions for built environments, what they could be with these new resources. For this research, complexity research that I'm directing currently is looking into imminent population growth, and so high density residential environments, and how we can build them to also provide high quality, democratize high quality design for everyone. So not only high density, but high quality city environments. And part of the reason why I started this research is also because I looked into many of these new applications we see, for instance, for developers and in city planning, such as Delve by Sidebox Labs, by Google, basically. So applying artificial intelligence to, for instance, develop quick feasibility studies. So it's really radically accelerating access to feasibility studies and showing developers multitude of options, what could be done on the site. However, in this case, machine learning is applied to databases or data from the current market. And we all know that the current market has lots of issues, and it's actually, it has some detrimental effects already to the cities. So my worry is that if we put it on steroids and somehow accelerate it with some of these new applications, that we might create new cities or conditions in our cities that are even worse than what we are experiencing now. So I think it's incredibly important what kind of questions do we ask of AI, of these new tools. And so starting quite differently than that approach, starting almost from a primordial states of architecture, looking into certain ingredients and then using computational petri dish of computation to somehow come up with the new states, initially primitive states of these new structures of high density, looking into, for instance, construction, automated construction and mass timber prefabrication, thinking obviously about also ecological issues, CO2 footprint, etc. And looking at this kind of combinatorics, something I've been working on for a long time. In a way, one of the basic principles of complexity, simple input, complex output. So for instance, looking into building block that is the same building block, only one, but it can connect to itself in 78 different combinatorial states. So this is an exponential and very quickly becomes big data problem and necessitates use again of machine learning to work with. Or looking into similar logics for automated construction and robotic construction. I was directing a quite large program in London at UCL at the Bartlett. So we had different research labs. This is one of them, looking into robotic construction, different forms of it, and different forms of different materials, different building blocks, different methods. Also, for instance, self-assembly, robotic self-assembly and AI. And then certain structures and architectures start to emerge out of this, but also resonating current cultures and economy tendencies towards shared economy, cluster living and working, co-working, co-living, etc. So starting to develop some of these schemes, feeding the platforms with that knowledge. And so the complex city platform that I mentioned just a minute ago is being structured to this kind of patterns of correlations or logics that can then absorb different data. And starting with just the basic combinatorics, trying to increase the resolution of, for instance, a tower or a high-rise in skin. If you have more skin, if you have more facade, you have more windows, you have more views, you have more exterior spaces. So the quality automatically starts to rise in these different units. So then you just feed these fitness conditions. I want the maximum number of, for instance, roof terraces in this tower. What's the maximum number we can achieve? I want really good relationship with dynamic complex forces of weather, for instance, wind. We know that that's a huge factor concern in terms of structural performance of high-rising buildings, but also, for instance, things like noise or wind tunnels in the dense urban environments when we have many towers, or for instance, exposure to the sun. So sculpting with data and pre-sculpting the field, the vertical field for maximum exposure to light, to the sun. And then these combinatorics of residential mixes, different ones. We use K-means clustering here, a form of machine learning that is then searching different combinatorics of those and giving us different qualities of these buildings. And then going into even higher resolution using yet another form of machine learning, in this case, self-organizational maps. So trying to render certain more subtle qualities in the floor plates of the apartments. And we just started this research recently, but I'm very excited about that, because if we could, for instance, render or start seeing certain properties such as atmosphere that in the past we were not able to quantify, and how you achieve, for instance, good atmosphere, just as an example, in every apartment through this kind of high resolution ingredients and machine learning helping us perhaps see certain things that we'd never seen before. That is what is exciting to me. If actually with these new methods, again, we render something invisible, visible. And also, I could give the whole other lecture just about this part, but with self-organizational maps, interesting thing is this kind of multi-dimensional data sources. So you get different, it's a really resilient platform because you could get different data inputs from all sorts of sources. The ones we just started with are maybe the most obvious and the easiest to engage with. But of course, we can work with myriad of other data in the future. And then all this data that is coming from different scales and sources are being percolated into certain lower dimensional data, which is just at the moment producing this kind of combinatorics, architectural tectonics. And yet what is also very good is that the topological relationships are preserved, so we don't lose information. And then these kind of tools that we develop with PhD researchers and collaborators are then given to students, master students of architecture, to search to quick design speculations. So what I would say is interesting is that not only that we are using machine learning for optimizing different performances of different systemic features of architecture, but also design process, creative part of design process is being automated through AI. And so human designer is accelerated, I would say, and could discover new dimensions of what was never previously possible. And in this particular design studio, we were looking into scientific hypotheses such as Halford one, where if we want to preserve 85% of the species, we need to leave 50% of the planet to the wilderness. So certain design ideas or planning ones, how do we engineer high density and wilderness in the same territory? How do we design these ecologies that are so close together? And so students are then with this new design partner, which is AI, almost having a more intuitive and very fast conversation, because they are able to check lots of different scenarios very quickly. So in this case, introduction of vertical green and extremely high density, pushing the system to the limits, and looking into these tendencies that I was mentioning of shared economy, of distributed and localized green energy production, of Industry 4.0, coexisting with living. So all these systems coexisting and being sculpted through this kind of big data, AI-assisted territory of design search. And so providing these visions of what high density, high quality cities could be, or even taking the same logics, the same automated tools into landscape conditions, or in this case, extreme environments, looking into Mars, different physics, different geography, etc., and looking into ideas of seeding life on Mars in a sense of preceding certain infrastructural systems first in a very high density, because they are non-human, so they could be they even could be packed at extreme densities within these host environments for energy production and storing, for instance, growth of biomass, etc. And then using that experience and transposing it to problems back on Earth. So, for instance, looking at extreme problems such as over 60,000 abandoned mining sites in Australia, these striking monumental machinic landscapes, and in desperate need of remediation, but also reinvention, what these sites could be in the future. And there are so many of them. So really working with these fast AI tools to be able to imagine different futures. So for instance, from the more classical ones targeted at human inhabitation, so looking at working very tightly with the site conditions, and then introducing, for instance, smart farming and energy production, and certain communities densely packed on these locations. Or more likely looking into certain non-human programming, for instance, new technologies and how we can engage these sites for new economies. So can be imagined green energy generation on this site. The sites are very good actually for that purpose, because they're usually very large. They already have existing infrastructures. Australia has highest amount of solar exposure than any continent, including Africa. So then looking at this massive scale infrastructural projects even, and using big data for context sensitivity, AI, concepts of new technologies, and activating those sites. Example of Argyle Diamond Mine in Western Australia, used to be the biggest pink diamond mine in Australia. In fact, worldwide, the biggest 90% of worldwide production of the pink diamond was coming from this mine. And then again, looking at local data of wind patterns, solar patterns, and then unleashing the design process that is highly informed, and is able to, again, binding micro to macro conditions, vast ecologies that we can now imagine. And we all know that planet is in peril at the moment. So it's interesting to think what kind of projects can we envision. And we did some feasibility studies in this extremely productive projects, potentially producing much more than fossil fuel-based economy that Australia has been relying on for such a long time. And I cannot, in this context, not mention this. Sometimes the projects that we are working on remind me of these Aboriginal paintings, but also Aboriginal culture and practices that Aboriginals have been doing. It's probably the biggest design project on Earth. Their management of the whole continent historically, that has been so successful in working with complexity, with ideas of complex systems, and ecology, and that I think we could really learn from. So, so again, I feel that today I just wanted in this brief presentation to give you some glimpses of possible futures, worlds that are not quite yet computable. I spoke to many computer scientists, and when I talk to them about the ideas that we are working on, they're always telling me it's not possible to compute this quite yet. But I think it's interesting to start to look into facets of these various problems, but from the principles of deep ecology, and be really curious what these new tools, such as AI, this new cognition, I would say, new partnership, can bring us, and allows us to ask what kind of built worlds can we envision or construct, and how our industries can be transformed through it. So can we imagine design proposals? I think we could, for the first time in history, of unprecedented nature, complexity, and scale. Thank you.